HARTU is a project funded by the European Union in the Horizon Europe framework. The project started last year in January, so January 2023. So we are still in the first part of the project, and the acronym stands for Handling with AI-Enhanced Robotic Technologies for Flexible Manufacturing. In a nutshell, the goals of the HARTU projects are to push forward the robotic automation in the manufacturing industry in Europe by combining soft grippers innovation, so robotic grippers innovation, and AI-enhanced technologies, AI-enhanced tools. By putting those together, the goal of the project is to make robotic automation more flexible in the manufacturing industry. We are trying to address a very specific need of the manufacturing industry, that is the ability to seamlessly switch from one product to another product without having to rearrange, reprogram, modify the whole automation lines. This first webinar is focused on one of the technologies, of the key technologies of HARTU, which is the, in this case, the electroadhesion soft gripper, or the innovative grippers with electroactive contacts. I'm going to tell you during my first presentation, especially where this technology comes from and why this is useful for the industry. Then there will be follow-up webinars that will talk about the other technologies, because HARTU is a big consortium. We have more than 10 partners, and each partner brings some piece of technology that then at the end will create a whole ecosystem that will enable this innovation to happen. So I'll get started with my presentation. Then there will be, so I'm going to talk about electroadhesion soft grippers more from the research side. So where this technology comes from, what is the research behind it? Why are we the people pushing this forward? What's our background? What are the innovation, the inventions that we developed that make this technology now ready to have a maturity level such that it could reach the market in a few years. And then there will be my colleagues at Omnigrasp. So Omnigrasp, I am the CEO of Omnigrasp SRL, which is a startup company that is specialized in soft grippers that use electroactive contacts, in particular electroadhesion. I'm the CEO and the founder of Omnigrasp. I am also an associate professor at Politecnico di Bari, which is a university in the south of Italy. Following my presentation, there will be the presentations of my colleagues Davide Grasso and Fabio Gargano, who are two engineers of Omnigrasp, that will tell you in practice what these grippers look like. So if you want to buy one of those grippers and it comes to your place, what does it look like? How can you install it on your robotic arms and get started with it? And then there will be my colleague Simone De Carolis, who is a researcher at Politecnico di Bari, telling us more details about the HARTU project. So we will discuss the starting points, myself and David and Fabio, and then Simone will tell us where the HARTU project will bring us, because the project started just a bit more than 1 year ago. So we won't be discussing a lot about the developments, what the results already of the project, but rather the starting point and then the goals of the project and how we will get there. Okay, I'll get started with my presentation now. So few words about myself. I'm a mechanical engineer by training. I've got a PhD in biorobotics at Scuola Superiore Sant'Anna, Pisa in Italy. I worked as a scientist at EPFL for 5 years, where I started to work on electroadhesion in 2 of the world leading labs on soft grippers with electroactive contacts that are the labs of Professor Dario Floriano and Professor Herbshay. I then started Omnigrasp as a result of the research developments that we've got during these years from 2017 to 2021. Omnigrasp was incorporated as a company in Italy in 2022, so it's a pretty young company. In parallel to being the CEO of Omnigrasp, I'm also an academic. I'm an associate professor now at Politecnico di Bari. I'm a an ERC grantee. I received the ERC starting grant from the European Union last year. So the project, my ERC started this year, and it's about artificial muscles, so a complementary but different technology respect to the one that I'm going to present you today. And I'm also a research affiliate at the Massachusetts Institute of Technology since 2022. So the problem that we have started addressing a few years ago when we started working on soft grippers with electroactive contacts is the fact that traditional robotic grippers are no good when we come to handling objects that are delicate, that are made with soft materials, as you can see by the scared strawberry on the left. And they also have a pretty hard time picking up objects that have widely variable shapes and sizes. And this is both these elements are important for the HARTU projects because we want to handle some objects that are soft in nature, such as vegetables, and we want to have flexible automation, which means that we want to switch from one object to the other, maybe the same day or even on the same automation line at the same time. So how can we solve this problem? So my background is in soft robotics. So together with my colleagues at EPFL, we started investigating how we can use a combination of soft materials, intelligence in the mechanics, what we call mechanical intelligence, and the use of clever physical principles such as the electrostatic forces that make it possible to create adhesion without the use of any glue. So an adhesion that can be turned on and off electrically. By combining these elements, so these electrostatic adhesion, soft materials, and what we know already for grippers, what we knew about gripper and grasping, we created this soft gripper enabled with electroadhesion that in this embodiment that you see in the video has two fingers. Each finger is a thin silicone membrane with electrodes in it. This gripper is able to pick up a wide variety of objects. And what's special about it is that it can do it without having to modulate the amount of force that it applies on the object, because the fingers are so thin and soft that there is no way they can damage the object. Even if the positioning is wrong, even if they hit the object, there is no risk of creating any damage or leaving any mark. At the same time, we engineered these electrostatic forces after many years of research to being able to lift heavy weights. So instead of just the few milligrams that we all know for electrostatic forces, we are all familiar with the experiments of rubbing a pen on our shirt and picking up tiny pieces of paper. Those are electrostatic forces. We use the same physical principles, but we engineered it such that we can pick up kilos. And that comes from a combination of elements, including materials, geometry, the understanding of contact mechanics. So as I was telling you, electroadhesion works like a glue. So when the fingers contact the object, we turn on the voltage on the electrodes that are embedded inside the fingers. And this voltage creates an electrostatic field that then, for how the electrodes have been engineered, it really works like a glue. So creates mutual attraction between the surface of the object and the surface of the gripper. So the two now can stick together and we can lift the object to pick it up. I was mentioning before that this has quite some background. So the first publication on this topic is from my colleague Junshin Take at EPFL in 2017. He made this gripper that uses a combination of artificial muscles and electroadhesion. This was a great innovation. And then when I joined EPFL, I started working with him and pushing forward this technology from something at very low TRL that was just a proof of concept to something more robust that could be used also in industrial scenarios. The second video that you see is one of my developments. I made this soft gripper so strong that we were almost breaking the rigid plastic frame when we were testing it. So it was able to lift unexpectedly kilograms of force. And I'm going to tell you why is this, what changed, why this became possible. Then we started studying contact mechanics, understanding things like peeling, and we added an extra degrees of freedom to being able to open and close the gripper so that we could always have the optimal contact, because we understood that was essential for being able to grasp the objects effectively. And then we'd also pushed forward the automation, integrated it in the robotic arms, and made a device that could actually perform some close to real pick and place. And then we created Omnigrasp. We started receiving funding. The first funding came from the Swiss National Science Foundation, and we created prototypes that are now more industry standards, are like TRL6 more or less, that can pick up large objects, can adapt to the different shapes of the objects, can be controlled electrically with a computer and microcontrollers. And this created some momentum then for the innovation that came forward. So we, this slide is just to tell you that we have quite some background. I would tell we are among, or probably the world experts on electroadhesion soft grippers. The technologies that we developed that we now have at Omnigrasp as pilots, so that we are implementing in industries already, come from over 10 years of university research. We have published more than 10 scientific articles on the topic that are widely cited. And then there is a little bit of a medal of honor. We published the world's most cited article on soft grippers overall. So not only electroadhesion soft grippers, but all kinds of soft grippers. It's an article from 2019, and it already received more than 1,500 citations, which is incredible. We have 3 patents on various technologies, and we are still patenting like at quite a fast pace right now, and we received several international awards. So let's dive a bit into the research that made all of this possible. So one of the key innovations, one of the key things that we understood for making these grippers so effective, because electroadhesion was known already since many years. There is quite a few labs in the world that use electroadhesions, that developed it, that made different ways of fabricating it, applying it, using it. But most of these grippers were not good when it came to pick up objects with complex shapes and different shapes and sizes. One key element that we understood was the role of peeling. So we understood that electroadhesion is, at the end, not very different from all the other kinds of adhesion. I worked with colleagues here at Politecnico di Bari, like Giuseppe Carbone, for example, who is an expert on contact mechanics. And we, for the first time ever, we put together those two worlds, the worlds of electroactive contacts, electroadhesion, and the world of contact mechanics. And we developed a model that we decided to publish because it was so good that we didn't want to keep it only for us at Omnigrasp, but we wanted the scientific community to know about this and to be able to use it. In fact, I've seen then many grippers after this that started to use also movable fingers, following up what we have developed and invented, because we understood here that by keeping by having the optimal contact angle between the electroadhesive and the object, we could change the force that we would generate by orders of magnitude, going from millinewtons that often people were having when they were trying to approach objects with a wrong angle, to kilograms. That is what we need in industry to do pick and place of objects. So this model was published in 2021 on Extreme Mechanics Letters, and it's also a highly cited paper. Then we went a step forward. This was with my student at the time, Massimiliano Mastrangelo, who was a PhD student at Politecnico di Bari. We moved this step forward to say, okay, if we have peeling, we understand now that the force is very low, so we want the fingers to be parallel to the object. But then what happens if we go underneath the object? And that was also another important understanding, that if we go underneath the object, then the physics changes a bit, and then we developed a model that explains why the force keeps pushing forward and actually increases exponentially with this angle of wrapping of the fingers on the object. And this is what made this possible, to this crazy stretching and huge weightlifting ability of this gripper that was from a few years before. So we observed this, but we didn't understand why that was the case. We couldn't model it. And then with Massimiliano, this was possible, and we published an article also on this topic. But then, so we knew that we wanted to wrap around the objects, but then what we started wondering was, how can we do that? We don't want to add actuators because that's bulky, that's gonna make the electroadhesive more rigid, it can damage the object, it can make the system more complicated. So can we directly use the electroadhesive to wrap around the object? And here came another very interesting study with Massimiliano again, and also Fabio Caruso, who is a PhD student just finishing now at Politecnico di Bari. And again with Giuseppe Carbone, that understands very well the interfaces between different objects, so the contact that there is at the interface. So we understood like how we can make the fingers spontaneously zip on the object, even at large curvatures, at small curvatures, so large bending angles, like the one that you see in the video, by properly designing the mechanics and the electrical part of the electroadhesive finger. And this was another very important breakthrough that, again, we decided to publish because we want the scientific community to know about this. And it made it possible for our grippers now to spontaneously adapt to objects of different sizes and shapes without having to add external actuators. So it's possible to design the fingers for a given curvature. So if we know that we want to grasp objects that have a minimum curvature of a given, or a maximum curvature of a given value, then we can now do so. And we decide how thick as to the dielectric needs to be, how long the fingers needs to be, how much voltage we need to apply in order for this to happen. So all of these technologies combined made it possible to develop these grippers that I was showing at the beginning that can adapt to a lot of different objects, that can go from small to large, heavy to lightweight, and made of different materials, from plastic to food material, metals, cardboard. And I mean, this is really remarkable how adaptive it is and how robust it is also. So this demo here, the gripper is basically blind. So it's grasping objects, just adapting passively to its shape and size. We are only telling it where the object is and how much it needs to close, but very roughly. And that's it, no sensors, no feedback loop. Then, of course, we want sensors and feedback loop. Now we are developing them. And for example, they are part of the HARTU project. But of course, as you can imagine, it's much easier to sensorize and make smart a gripper that intrinsically, mechanically, by its own physics, can adapt to the object, rather than something that if you don't put a bunch of sensors on it, it's just going to crush your object. And so you have to be very careful with your sensor. You need very high computational speed. While in our case, for our grippers, it's relatively easy to sensorize them, because just a little bit of extra smartness is enough to make those grippers really adaptive and intelligent. So here came a first project funded by the European Union, which is the Merging project, that we kind of joined in the middle because one partner left, and then we were the ones that had the right technology for the project. So we joined 1.5 years ago, and the goal of this project was because the project is finished. It was closed at the end of last year, to bring back help bringing back some manufacturing to Europe in those fields where there has been a lot of outsourcing to developing countries because of the intense labor that was required. In particular, one of the industries that we focused on is the textile industry, where robotic automation is pretty difficult because picking up textiles is very hard. This example in the video here is one of the use cases that we focused on in a company called Selmark in Spain, and this was coordinated by our partners at IMEN, that are one of the technology providers of this project in Spain as well. So the use case here is grasping stacked textiles and doing machine tendering. It seems pretty easy, but the very hard part is how the hell do we grasp a stacked textile? How do we grasp a piece of textile when there is other textiles underneath? That's very hard for a robotic hand. And we thought electroadhesion would come at hand here, would make it possible to do this kind of difficult grasping. So when I was at EPFL, when this was developed initially with my colleagues Herb and Krishna, we invented this method for grasping where we use electroadhesion only to lift one of the corners of this textile on the top, which is something that electroadhesion can do very well. It's very difficult to lift the whole textile unless we use a rigid gripper that is the same size of the textile, because the electroadhesion pressure that we can have on textile is not very large, because you know how textiles are. There is not a lot of density of materials. They are pretty empty. So electron vision need to grab on materials, and if there is no material, there is nothing to grab on. Then we found this way around where we only grasp a corner. You can see a video here that shows how this is done. And again, by our understanding of peeling, we designed the kinematics of this motion. This is something that is we deposited a patent on. The kinematics of the motion, so that the peeling wouldn't happen and wouldn't let the corners slip down. And then after we peel the corner, we are now able to pinch the textile, and at that point, after pinching, everything becomes a piece of cake. It becomes easy to move the textile around as we would do with our hands, as the operator does at the moment. And so we demonstrated that it was possible to pick up textiles of different sizes and shapes. And since it's on the corner, the textile can also be all crumpled, and we can actually open it up. It doesn't have to be nice and flat to start with. But there were some problems with this gripper. As you can see here, the kinematics is not very well developed. The connections are, well, as you would do in a lab for a demonstration. The kinematics is such that we can also only pick up from the corner of the table. So this was no good, of course, for industrial use. Then we push forward the innovation here at Omnigrasp during the project merging, and we created a different kinematics that can now pick up from any point on the table. And the gripper was industrialized. It was made more compact with connections all included, made robust so that we could last for thousands of cycles. And this is work done by my colleagues at Omnigrasp, Fabio, Davide, and Massimiliano, that at the time, then after his PhD had joined Omnigrasp. And the results were fantastic. We were able to pick up a wide variety of textiles and to pick up them from any point on the table and repeatedly. So now we can pick up even stitched textiles, and we can separate layer by layer. And this is one of the examples of the testing that we did. We designed an automated testing setup where we could test for thousands of cycles and check that the system was robust and repeatable. Finally, at the end of the project, with our colleagues at Timon and all the support from the other partners, we integrated this at the facilities in Selmark, and we demonstrated that it's actually possible to do the machine tendering that we were supposed to do with this project. So you can see here that we separate a piece of textile and do machine tendering inside the heat press. And here is another example with another textile. So here there was a big step forward being made also for the integration, because one thing is developing one device, another thing is developing the device and making sure that it can talk with all the rest of the system, with computer vision, path planning, robotic arms, the machine that we have to operate. So everything was put together in a nice system, and we demonstrated it could work well. And this is something similar to what we are working on now for HARTU. So developing a gripper for different use cases, but can then also fit in an ecosystem with all the different technologies developed by the other partners. And this brings me to HARTU, that, as I was mentioning before, it started at the beginning of last year. Here is all the partners that form the consortium for this project. One of the use cases we are focusing on, we are back on food now, so it's a pick and place of fruit and vegetables. And what we are planning to do with this project is to obtain seamless adaptation to different objects, so that, as I was mentioning before, we can get flexible pick and place in manufacturing. So it's possible to change from one object to the following one without having to replace, adapt the gripper, or to reprogram the automation line. And also we want the gripper to be smart, to be able to recognize the objects and adapt its grasping posture based on the different objects and where they are positioned. And this will be done by integrating the AI technologies that the partners are developing. This brings me to conclusion. I want to say big thanks to the Omnigrasp team that made all this work possible. I'm lucky to be working with super smart and creative people. And that's the end of the talk. Here are some of my contacts. If you wanna get in touch, we have positions open, so reach out if you're interested. I can see I'm in time. I was even faster than expected. That's always great. So let me conclude and leave space to questions.
Yes, if you have any question, you can write it in the chat, or if you want to ask directly to Vito, you can unmute yourself. Maybe first you can raise your hands so we can see who you are, and then you can unmute yourself if you want to intervene. We have 50 minutes of question and answer, so please, if you have something to ask, do it now.
I can see there is a raised hand by Nicholas.
Okay.
Marta, are you giving people the right to talk? How is this working?
Yeah, they can themselves and
Ask
then
directly. Okay.
Yes. Okay.
There is also another one.
Gennaro, you can.
Okay. Good morning, Vito. I would like to ask you if so there is the possibility to sell these grippers or to try. Are you already industrializing them?
Yeah, I mean, what you have seen today is not all what we are, what we have, of course, at Omnigrasp. This is what we share mostly, so it's the most public part. But yes, we are doing pilots with something similar to what you have seen, and also modified versions, different grippers. So if you think this can be interesting for your for your industry, I don't know if you, I can see your affiliation. Are you part of a company? Are you asking it for a use case?
Yeah, I'm working now for Eurecat in Spain. I think it's also part of HARTU project.
Oh, okay, nice.
Yeah.
Okay, great. Yeah, well, get in touch. I mean, we are doing pilots now, so it's not yet a kind of off-the-shelf product. But if you have a use case that can be a good matching, we get in touch. We can come at your place and see if one of our grasping technologies is well suited for your use, and then we set up a pilot together. And so you can test it, and if you're happy with it, then we can talk about scaling it up.
Yeah, we have many projects in fruits handling, so maybe I will talk to my supervisor. See.
Great.
Thank you.
Thanks for the interest.
Thank you, Gennaro. Nicholas had some problem with the microphone, so he wrote the question. He was wondering if electroadhesion is applicable underwater.
Oh, at the moment, no, it's not. So short answer is not. If Nicholas has some interesting use case, we can have a chat. That we had some thought about how we could use this underwater, but it's something more longer term. So as they can't be used underwater. Research-wise, it's a development that we were thinking of, but it's more longer term. So it's gonna take a few years of research. And I mean, there is alternatives underwater in general. So, but if there is the case that this seems pretty interesting for some reason, let's have a chat. But as it is, it's not.
Okay. And okay, so he said that he will get in touch. Shifan asked
Gaspar
what
had a question also.
Yeah.
Yeah. Hi, Vito.
Hey, Gaspar.
First of all, thanks for the fantastic presentation. Very impressive work. I'm
welcome. Thank you.
Totally impressed. Just wanted to know what the limitations are of your grippers. They're very so you showed that they can handle a lot of different objects, different shapes, but are there limitations if they are, for example, edges on their curvature is too high, in other words?
Yeah. Indeed, yes, yeah. There is, of course, limitations. Curvature is one of them. So that's what you pointed at. It's one of the challenges that we are facing. So it's important to know if there is sharp edges, because as I was showing before, zipping, it's something important. We want the fingers to adapt to the shape of the object. That depends on curvature. So if the curvature is extremely high,
then the zipping is going to stop. It's not going to happen anymore. So this is one of the limitations. Another one that, as you can imagine, is the fact that we want soft fingers because we want to be able to conform to the shape of the object, but then this makes it difficult to rotate the object, for example. So if the object is heavy, we can't do that very well. So that we are looking at a trade-off where we can still have the flexibility that makes it possible to adapt to the shape of the object, but then the fingers can be also rigid enough, not only in the vertical direction, because that's great, that works well, but also in bending, so that at least globally we can transmit some torque to the object. That is what we need to rotate it.
Yeah. I hope it's okay to ask another question. You showed some images. Thanks. You showed some images where you would like to pick up fruit and vegetables that are, thrown into a crate next to each other. Your grippers are very flimsy, very soft, but sometimes it might be necessary to actually be a bit more stiff to go in between two objects and then to apply the forces that you apply to pick things, an individual item out of a box.
Yeah, that's a very good point. Yeah, that is something that with the current gripper we have a hard time doing. So we are working on a development there. And one of the options is, as you mentioned, that again finding this trade-off between being soft enough but not too much, so that we can transmit torques. Is one of the reasons why we want this. And another reason is being able also to go within objects, so that we can actually pick them from the sides if needed. So that we are working now on within the HARTU project to solve this issue, and being able to pick up objects also in that kind of packed scenario that you correctly identified.
Okay, yeah, but very good. Thanks a lot. Thanks.
Thanks for the interest and for attending.
Thank you. We have Shifan who is asking, what is your product benefit compared to suction cup?
Yeah, so suction cups are great. There is a few benefits with respect to suction cup. One of them is that you don't need suction, so you don't need vacuum lines. And vacuum lines are great. I mean, if you have them already, great. Most industries do. But if you want to bring automation to an industry that doesn't have automation, then having to create all the suction line pipelines and the pump and where you put it, the compressor where you put it, all the valves, it's kind of expensive, it's noisy, it's bulky. So what we have is fully self-contained. So it's just what you see in the wrist. It takes a 12-volt input, GPIO or USB for data transmission, as my colleagues will show in a moment, and that's it. So it's much simpler to operate, it's self-contained, less expensive, and also less energy hungry. So it consumes much less power than suction cups.
Okay. We have another question. Is there any limitation on the object surface? Can you pick delicate fruit like strawberries?
So it can pick delicate fruits, no problem. Strawberries are one of the most challenging because of the surface, so that's a good point. We like strawberries, but the fact that the surface is hairy, it's always historically always created issues. And it's been a while that we haven't tried strawberries. So with the improved grippers, it will be worth trying. But yes, there is a roughness range, which is very wide, but still it's a range. So if things are extremely smooth, then we can have issues letting go, because we have dry adhesion that dominates and makes the release difficult. And if objects are very, very rough, like a kiwi, for example, then we can have issues picking up, because the roughness, if we have a very large roughness, like a hairy surface, then it keeps the fingers far away from the bulk of the object and makes it difficult for the electroadhesion forces to establish.
Okay. And then we have Jawad, one of our partners, who is asking, is your gripper CE marked or other compliance certified? Are you planning to obtain some certification in future? What are the barriers?
Yeah, that's a good question, Jawad. We don't have the certification yet, but we are working towards certifications. There is a few things. So, for example, we are now designing grippers that are like that have a certain level of IP that's important for getting certification that we use. Then it depends on the kind of certification. Like for food, for example, IP is important, materials are important. So it's something that we are working towards right now. I don't see many barriers, if not just the engineering required generally to move from something that is a research prototype to something that is a certified industrial product.
Okay, thanks. And then we have Sima Lasif, who's raised the hand. So if you want to talk, please.
Yeah, I'm Dr. Sima Lasif, Senior Lecturer from Cranfield University. Interestingly, I'm working on the... Can you hear me?
Yes.
Yes, yes.
Okay, yeah. So we are working in the Intelligent Robotics in Automation Lab in the Center of Robotics in Cranfield University. We are also part of Made Smarter project for the smart robotics, through which we are working on the on various gripping projects, but those are for the complex manufacturing parts. I was wondering how the gripper, you have shown us great presentation, great work behind that. I was wondering how it work with different materials. For example, it's wood, metal, different surfaces, complex manufacturing parts. Or do you think, and then I'll go for the second part of the question, if that's okay.
Okay. Yeah. So let me answer the first part then. So it's a great question. The different materials are surprisingly wide. The range of materials we can grasp are surprisingly wide. So we can go from plastic to metal, going through paper, food. Like there is no intrinsic limitation in the material. It can be conductive, can be dielectric. That's not a big issue. The surface is more important. So if the surface is very rough, so if you tell me wood, if the wood is smooth, no problem. If the wood is rough, like a piece of wood that you can hand cut, then that's gonna give us some problem because the roughness is gonna be very, very large. Mm-hmm. So it's more about the surface. And for complex industrial manufacturing parts, as you said, this connects a bit to Kaspar's question before. If there is objects that have a lot of cavities and sharp edges, those become a bit difficult. We need some surface to grasp because it's a surface-based grasping. So it's not like hook-based or pressure-based. So we do need a little bit of surface to anchor. So that depends a bit on how heavy the object is and how really complex those shapes are. We can handle complex shapes like bell peppers. Those are really pretty complex. We show them, we choose them because of this shape. It's pretty nice and difficult to pick up otherwise. And also those are complex materials in the sense that if you push on them, they're going to deform, and this makes it challenging for traditional pressure-based grippers to grasp them because the shape is going to change while you grasp it. But then if we are talking about something that is like I don't know, like a keyboard. I was thinking this morning about a keyboard. A keyboard would be pretty difficult to grasp with these objects because there is basically not enough surface at any point where we can actually attach.
Yeah, the second part of the question was around the orientation of the object. Do you think it's important aspect?
Well, yes, orientation is important indeed. Well, orientation before grasping also has some importance because especially if we are talking about the two-fingered gripper, the one that I showed in a big part of the presentation, that gripper needs to go on the sides, or if the object is heavy, even a bit underneath the object to have enough force to lift it. So depending on the shape of the object, this might be more or less difficult based on its orientation. And then the second part of that is changing orientation. That's, as I was saying, is one of the things that we are working on at the moment, making the fingers stiffer so that they can transmit torque.
So, for example, if you have a banana, a large banana, and you are not lifting it from while it is laying on the flat surface, if you want to grasp it from the top, how do you think it's it is going to be able to it will be successful in doing so, or?
I don't think we would try to grasp it from the top. No, it wouldn't work. So the top is where you would try to grasp it if you have a pincher-based gripper, because the top is the hardest part. So you can pinch on that and you can grasp it with a pincher-based gripper. But without gripper, you would actually go on the side wherever there is some surface. On the bananas, we grasp them pretty well. We tried a few times, and in that case, orientation is not too important because most of the times you can still access some of the surface of the banana, so it's possible to grasp it, but not from the top.
Have you thought about going to the hybrid in order to widen the range?
Yeah, that's a good suggestion. We thought about it. So far, we haven't done it for a few reasons. Well, it's not a simple hybrid. So hybrid can be done in many ways. One way is you just have the two grippers and you can choose which one to use based on what you want to pick. And that's one approach. Another approach is to have an hybrid where you have actually an integration. So for example, having electroadhesion skins on rigid fingers. This is something that we are exploring in HARTU, but it's not that easy because they don't work. It's not like you just take two things, you sum them up, and the result is the sum of the two parts. They couple with each other. So the performance of the electroadhesive especially is going to be affected by the fact that you have a rigid pincher-like gripper underneath. So this needs some more study and exploration for being done. But it's something that we thought about, and it's also something that we are exploring in HARTU.
Very interesting. Thank you very much for your answers. I'll definitely get in touch.
For your questions.
Yeah, thank you.
Please do. Thank you.
Thank you. I think we can move forward. I saw other questions and other hands raised. We can address all the answer at the end of the webinar. So don't panic. A question, and then we can address them. So we can leave the floor to the next speakers.
Good morning, everyone. I'm going to share my screen. Can you see my screen, right?
Yes.
Yes.
Okay, good. As I said, good morning, everyone. My name is Davide Grasso, and I'm a mechanical design engineer of Omnigrasp. And alongside me, there is my colleague Fabio Gargano, that is a mechatronics engineer of Omnigrasp as well. So in this presentation, I will be showing you the structure of our electroadhesive gripper, along with providing the detailed step-by-step instructions on the unboxing and the assembly. This will enable you to easily start your pick-and-place task with our cutting-edge gripper. So, upon receiving our gripper, you will discover a thoughtfully compact packaging that efficiently houses the essential components. Inside, you will find the electroadhesive gripper, the communication cable, and also an AC/DC converter.
I don't see your screen anymore, Davide.
Sorry, I don't know what happened. Maybe.
Try showing again.
Yes. Like this. Okay. Can you see it?
Yes. Thanks.
Okay. So I was talking about the communication box and cable, and also the AC/DC converter aimed at continuously supplying power to the communication box. While the cable is provided as an added convenience, it's worth noting that it's not mandatory, as the gripper can also be controlled using the internal cables of the robot. Some of the advantages of our gripper are the lightweight, weighing in at less than half of a kilogram, encapsulating all of the electronics and mechanical installation parts inside of it. Its compact dimensions, akin to a cube of 11 centimeters per side, ensure a minimal footprint in any global application. This is an animation of the assembly on the robot. The installation process is smooth and fast, consisting of just 4 straightforward steps using the components that we provided with the packaging. Now we can have a look at the manual installation done step by step. Starting by placing the robot adapter on the wrist, aligning the holes, and securing it with the bigger screws, using a screwdriver or an Allen key. Following this, place the gripper on the adapter, according to the cross path on it, and secure it with the smaller screws. With these steps completed, now the gripper is ready and ready to be connected with the controlling computer. The next steps involve connecting the communication box with the electrical line through the AC-DC converter provided, then plugging the communication cable's female end into the gripper's male port, fixing it with the nut provided in the gripper's male port. Subsequently, connect the communication box, and this step establishes the link between the gripper and the controlling computer using a USB Type-B cable. This configuration facilitates a seamless control on and the operation of the gripper directly from the computer. As you can see, the installation procedure lasts less than 5 minutes, and it doesn't need any kind of expertise. Now we are done with the physical installation, and we can have a look on practical mounting. Our robot adapter offers adaptability for installation on any robotic arm. Let's take a closer look at the gripper's adaptability through examples of previous mounts on different robotic arms, such as the UR5 bot directly linked to the wrist or to a custom-made plate made in the company, and also the FMPP Robeco. In all of the 3 cases, we can easily mount our gripper. Each robotic arm presents its unique dimensional constraints. We can create a custom-made robot adapter in less than an hour once we were aware of your dimensional constraints by rapid prototyping with 3D printing. After giving you a sneak peek into its assembly, let's uncover the fascinating wonders concealed inside together. As you can see, the components are numerous, each playing a specific role crafted through extensive mechanical study. For example, the TPI interface combined with the electroadhesive features make the gripper soft, proficient in handling fabrics with the utmost care, leaving them unharmed. Now I leave the floor to my colleague Fabio, who will guide us through the gripping operations and control. One moment, I switch off my audio so Fabio can have the control.
Good morning. Can you hear me?
Yes.
Yes.
Okay. Can you share my screen?
We see your screen.
Okay. Here we have an example of a operational setup configuration. The gripper is mounted on the robot wrist and ready for use. The black case encloses the power electronics within the gripper. The communication between the gripper and the PC allowed through an M8 cable, which transmit input and output signals. This cable is connected to the box shown at the bottom right and labeled as the COM box. The COM box allows communication between the gripper and the PC and also acts as a power supply. Sorry. Here we see the communication protocol. The communication protocol used is a ROS, Robot Operating System. The ROS structure is very simple and represented in the figure I'm showing. We have a ROS master responsible to synchronize the gripper state with the robot movements. The master communicates with the gripper using a serial protocol and with the robot using a TCP protocol. The ROS framework makes it easy to integrate different software and hardware components, allowing the integration of multiple robots as well as computer vision or artificial intelligence. These are the primary components that define the communication and power supply system of the gripper. The electronics control are completely housed inside the case, enabling communication through an M8 connector placed on the side of the gripper. The cable has two main lines, one for power and other for data. This cable is connected to the communication and power box, which has two connectors on its side. The first connector on the right is a jack connector used for input voltage, 12 volt. And the second connector on the left is a USB-B connector, essential to allow the communication between gripper and the Roastmaster. You can install the Roast package in a few simple steps. Just access to GitHub repository, use the git clone command to copy the folder into your working environment. Then install the package, and now you are ready to control the gripper in your terminal. Here you can see the main topic to control the gripper. Through topic voltage and frequency, it is possible to adapt to different textile. With the topic state, we can control the gripper state on-off, and with finger, allow to move the finger open or closed. To start using the gripper, connect the power to the box, and after connect the USB cable to the PC. Now connect the gripper and launch ROS. So the gripper is ready for use. In this window, we are running the demo file, allowing activation and deactivation of electroadhesion, and opening and closure of the finger. This can be done interactively using a command for PC keyboard connected with ROS. Now we see a practical application of demonstrator. Explore a successful case from the merging project where the gripper was correctly integrated at the Selmar facilities in Vigo. Particularly, we can see, start the video. Particularly, we can see how the Roastmaster coordinating two robotic arms that work simultaneously. The computer vision recognizes the position of corner textile, then both robots move to this position. Now electroadhesion is on, and the gripper grasps the fabrics. After this, the robot puts in the thermoform the textile and release it. Now I leave the floor to my colleague Simone. Thank you very much.
I think we have a Q&A before we move on to Simone, or is it directed at the end?
Actually, we have it later, Vito. So
okay. Sorry, Simone. Yes, please go ahead.
Don't worry. I hope you may hear me. I guess yes, and you can see my screen. So good morning to everyone. Let's move on to the final part of this webinar, where we'll sum up the goals of the HARTU project. I am Simone De Carolis, a researcher at the Mechanical Engineering Department at Politecnico di Bari, and together with Omnigrasp, we are trying to bring into HARTU our knowledge in contact mechanics, modeling, and design of electroactive grippers, as Vito showed before. So, our aim is to assist European manufacturing companies in transitioning towards Industry 5.0, also known as collaborative industry. And therefore, this talk will outline some of the goals pursued by the HARTU project to facilitate this kind of transition. After providing a brief overview of HARTU and describing some of the industrial scenarios we are working on, I will highlight the roles of Poliba and Omni in the project before concluding by outlining the expected results and outcomes. Let's start by recalling the meaning of the acronym HARTU. HARTU stands for Handling with AI-Enhanced Robotic Technologies for Flexible Manufacturing. So this means that HARTU is an industry-driven research project focused on solving the main challenges related to handling parts in manufacturing lines using new grippers which want to be enhanced with artificial intelligence control. The project aims to apply this innovative solution in real industrial scenarios to develop tools that can handle various products regardless of their shape, materials, or size. In the figure, you can see some of the products that are part of the project case studies. These range from typical mechanical components to those in the consumer goods industry and even food products. Such a wide range of products already illustrates the primary aim of the project. So to offer a solution applicable across much of the manufacturing sector, which is vital to Europe due to its large number of enterprises, jobs, and also for its significant impact on the European Union GDP. But why focus on handling technologies? The reason is simple. Over 80% of operation on production lines involve pick and place tasks, which can be carried out by either humans or robots. However, conventional industrial robots are often limited by specific features for each component. So this makes it difficult to perform transition to more flexible solution where a single gripper can handle various types of objects. So flexibility is one keyword of the project, and it's driven by recent trends in mass customization and e-commerce, which demand us a wide variety of products in small quantities. And these also add challenges in standard ad hoc programming for manipulation tasks. With HARTU, our aim is to address the need for flexibility in manufacturing. We'll achieve this by developing new gripper concepts based on electroaddition, which also take benefits from AI learning techniques. These technologies will continuously adapt to the task at hand. Additionally, what we want to do is to bring recent scientific advancement in soft materials to the industrial world. By doing so, we hope to improve the adaptability of manufacturing processes, making production lines more flexible and efficient. The aim, so, is to develop an effective and intelligent AI-enhanced system that can overcome the difficulties associated with the complexity of various working environments. So one system that can learn and improve its capabilities over time. Here are some key numbers related to the HARTU project. It spans a duration of 3 years, starting from January 2023, and involves collaboration among 14 participants, including research organizations, system integrators, and communication experts. Among these participants, there are 5 manufacturing companies, with 3 based in Europe, 1 in Turkey, and 1 in Taiwan. The project focused on 5 case studies covering different industrial realities, including automotive, consumer goods, logistics, and food industries. Over the course of the 3 years project, HARTU researchers will work closely with these 5 industrial companies, and they will study their production processes and develop innovative robotic components to enhance flexibility of production lines, which means to enable the same robot to learn to manipulate and assemble a wide range of objects. So now let's briefly touch upon some of the case studies, not all, but just some of them. Here you can observe one specific use case being investigated at TOFAS, involving the preparation of spare part delivers to dealers, which is basically a 2-step process. An operator retrieves parts from the warehouse based on a provided list and place them in a large box. And it's easy to notice how this classical delivery operation relies on human handling, basically. Looking ahead, we envision the implementation of mobile manipulators equipped with a vision system to enhance flexibility and efficiency in both kitting, assembly, and spare part preparation, let's say. This configuration offers versatility across different tasks. The transition is therefore toward robotic mobile handling. On the right, you can see, in fact, an initial scenario we are reproducing in the laboratories of Technical. As a second example, the use case in Ulma. Ulma provides logistic solutions, including automatic warehouses and pick-to-light technology. Currently, manual handling of item for their preparation is challenging due to various factors: the vast number of different products, lack of universal grasping tools, small order sizes, and so on. So in the future, what Ulma envisions is robots equipped with vision system handling order picking autonomously based on instruction from the warehouse management system. Last but not least, so let's go from automotive to logistics and then to a food sector case study. This use case focuses on optimizing processes in food warehouses, specifically sorting and packaging operation for a variety of vegetables. Currently, these tasks are performed manually, posing challenges such as high costs and potential hygiene issues. Looking ahead, the vision is to implement collaborative robots capable of handling vegetables of various sizes, shapes, softness, and so on, even when randomly distributed. These robots will operate safely alongside human workers. And so the aim is to develop a more efficient and ergonomic workspace like the one you see in the center of the slide, that is an early stage of the project at Techniker Laboratories again. And these are just a few of the scenarios within the project that already demonstrate how improving the efficiency of these manufacturing systems can impact the European economy, considering the sole production value of sectors like food, for example. The case study proposed by Tecnoalimenti represents for us an opportunity full of interesting research and development challenges. In fact, this project is challenging due to the features of the environment where bean picking is required. Factors such as variability of products to be handled, the unstructured environment, the complexity and the irregularity of surfaces to use to grasp, and also the very delicate nature of products suggests that manual handling may be the only feasible solution, or it requires the use of a gripper equipped with a lot of flexibility and also robustness. So new grippers equipped with electroactive fingers can fulfill these requirements, thanks to the use, as Vito was presenting before, of these compliant fingers. So electroadhesion utilize electrostatic force, which are gentle force, enabling the grasping of delicate object with simple control. In the demonstration video, you can already see the flexibility of a gripper equipped with electroadhesive fingers in handling objects of various shapes and sizes. Furthermore, the use of electroactive fingers enhances the functionalities of this gripper while maintaining relatively simple and cost-effective mechanics. These grippers are presented as tools that are noiseless, self-contained, low consumption, and versatile. In addition to these advantages, within the scope of the HARTU project, we aim to further exploit the potential of electroadhesive fingertips to more towards smart electroadhesive fingertips. On the right, you can see a demonstration of force measurement when handling soft object. The soft center is mounted on a two-finger robotic gripper and is used to measure the normal and the shear forces when grasping. We'll see it in a minute. So now the system is gonna grasp the water balloon, and in the meanwhile, you can see normal and shear force on this plot. Then you lift, rotate, and release this delicate object. And in the meanwhile, we have a measure of the two forces we need. As well, electroactive fingertips can be used as capacitive sensor like this. So they are potentially equipped with the mechanical intelligence. This offers the advantage of measuring not only contact with the object, but also electrical properties of the object, meaning that they can recognize the object being handled and adapt the force to its size and weight. Another feature that allows us to speak of the mechanical intelligence of electroactive fingers is the ability to switch adhesion on and off to control friction coefficient. This video, for example, demonstrates the utility of the tunable friction mechanism in two applications. This first one is the one of 1 degree, let's look at it again, 1 degree of freedom crawling robot to propel itself forward through asymmetric friction on the power. And the second one is a multiple degree of freedom soft gripper that uses friction differential on its fingertip to successfully screw in a light bulb. So this is our concept to bring in industries some advances in research, like the one of capacitive sensing and this one on tunable friction tools. Last but not least, the mechanical intelligence provided by the electroactive fingertips can be enhanced by combining the AI-based components from other pillars of the project. Some of the benefits that can result from this synergy are related to eliminating manual grasp programming through self-supervised grasp planning and simplifying robot training for assembly tasks using programming by demonstration and advanced control techniques for managing contact interactions. As we wrap up, let's reflect on the key points of the HARTU project. Our goal is clear: to speed up the shift towards greener and more digital manufacturing and construction sectors. We've been working hard to create production lines that are super flexible and efficient, perfect for making customized products while reducing mistakes. Our approach is open, making it easy for factories to use our technology. With HARTU, we're making robots smarter by adding artificial intelligence. This means that they can learn to grasp objects on their own and handle complex tasks more easily. But as we move forward, we're also keeping people in mind. We're focusing on how humans interact with these new technologies, making sure that they're easy to trust and use them. So in short, HARTU isn't just about fancy tech. It's about building a better, more sustainable future for manufacturing and construction. We started with a question that was how to pick almost anything. I would suggest the answer that is just with a great team such as the one in HARTU. I thank you all for your attention, and if you have any question for me, Vito, Fabio, and Davide, please.
Okay, so if anyone have a question, you can write it on the chat, you can raise your hand, and in the meantime, we can answer to the question before. So in the chat, Mahadi wrote, as could be seen in the videos, the gripper performed very nice to pick up objects vertically. How about picking items when the manipulator gripper is not vertical? For example, picking tomato or strawberries from the bushes? I think Vito can answer this question.
Yes, no, that is something still challenging to do with the current embodiment that you have seen. So that embodiment is designed to pick up objects vertically. We are redesigning it so that we can also pick from the sides. It becomes more and more difficult the heavier is the object. So if we think something like a strawberry is not too difficult to do. If we think something like an apple, it becomes a bit more difficult, and so on and so forth. But it's something that we are, as I was mentioning before, we are working on. The ability to transmit torques. It's something that doesn't work with the current embodiment, and that it's part of our research how to change the geometry materials to address that.
Okay, we have also Ajibo. who said, my question is with regard to grasping of food materials. Have you been able to try this product on the grasping of meshed food material?
No, it's not gonna work. So I think for meshed food material is not the right gripper. If you want to meshed food material, it's better if you use a spoon kind of gripper, or something to kind of envelop the material. There is pretty cool grippers done by some colleagues. There's a startup in Singapore that makes pneumatic grippers. They are very cool because they can close, forming a cage, and they can pick up granular material. I'm not sure about meshed, but it might also work. And then there is also a few colleagues in Japan that are making grippers that can pick up meshed food. Tradition is not a good technology for that. One would need another gripper for meshed food.
Thank you, Vito. And we have addressed all the previous questions. If anyone else has something to ask, please. We have 10 more minutes. Okay, question to Simone. In principle, could the capacitive fingertips work underwater?
Okay, nice question. I guess also Vito can support me, and I think that we should have the same problem we have in grasping. Okay, so when we say that we are able to use the electroactive finger tip as a capacitive sensor, is why basically it's just a capacitor. So we can integrate some simple circuit, measurement circuit, and I guess that for now it should not work in environment like water.
If I can add,
yeah.
I mean, there is nothing, that configuration of the gripper, the shielded soft force sensor, since it's shielded, there is nothing preventing it to being used underwater. So there is no, its working principle is going to work underwater as well. Okay. It's a force sensor that uses soft capacitors inside, and then everything is shielded from the outside. Of course, it's not engineered to be used underwater, meaning if you want to use underwater, then we need to make sure that the connections are all completely sealed and isolated. But the sensing principle itself, it can be used underwater. There is nothing preventing it.
Okay. We have Gennaro, who have raised hands.
Yeah, thank you. I would like to ask if now it is possible to have a feedback in force or in voltage, or if it will be possible in the future maybe to do a feedback loop.
If the question was for me, I've lost the initial seconds. Sorry, because I
sorry.
went out battery.
So I can try to say it again.
Thank you.
Will it be possible to have a feedback loop in force, or have some feedback in voltage from the grippers?
Yeah. So we have a feedback in voltage. It's possible to have a feedback loop in force if you add force sensors, like the ones that Simone has shown. So if that is added somewhere on the fingertips or higher on, then it's possible to have a feedback loop. So spoiler alert, in HARTU we are developing closed loop grippers. So the voltage is already there, and we are also adding now additional sensors to have a closed loop gripper, because at the end that's what we want. Depending on what you need specifically, we can have a chat on what kind of feedback loop you need, but it's something that is already, it's almost ready actually.
Okay, perfect. Thanks.
Sure.
Okay, any more questions? No? No, I think we don't have any more questions. I don't know if you want to wrap up the webinar.
Yeah, let's wrap up. That was pretty efficient. Good. Thanks everyone for attending. So numerous. It was great to see so much interest. Thanks to all the presenters, and thanks Marta and Erika for organizing. And of course, a big thank to the European Union for supporting HARTU and making all this exciting research possible. So for everyone who attended, stay tuned for other news from the HARTU project. We will be releasing the research advancements that us and the other partners do with LinkedIn and on our website. So if you are interested, get in touch and also stay tuned to our channels, and hope to see you next webinar.
Maybe a quick question from me.
Yes.
Will the video be available, the recordings?
Yeah. We can share it on YouTube, so please stay tuned, and we can share it all with the participant via email. So
Fantastic.
No,
Thank you. Yeah, and thanks a lot for the good webinar. Thank you. Bye.
thank you.
Bye. Thanks for attending, Kaspar. Bye, everyone.
Bye.
Thank you very much.
Thank you. Bye.
Bye.
Thank you. Bye.
No.